Hello, in the previous dynamic program video, we mentioned we want to ignore this example optimal binary search trees. Since this semester we are going faster than the previous semesters, we want to cover this one just to further enhance your understanding of dynamic programming. It's also possible, though we don't put this one as the assignment questions, but we may cover it in the final exam. So that means we want to provide more details about this algorithm. So the first thing is that we are talking about a binary search tree. What is a binary search tree, BST? So basically we want to arrange the sequence of numbers in a tree structure, and then we can search it quickly. So binary search tree has this property. So this is a tree, and then always the left one will be less or equal to the root, and then the parent. It can be the root, but it can be any further tree can further expand. So left is always less equal to, and the right one is larger or equal to. Okay, so for example, let's look at, for example, this is the middle is 5, and then this one can be 3, this one can be 1, and this one can be 4. Right? So this one is less than this one is larger than this one is less than this one. But you also can consider, so all the numbers on the left branch of this binary search tree must be less than this root, okay, less than this one. So this one we can get 7, okay, larger than this one. Okay, this is the basic idea, the binary search tree. So that means, for example, we can do this one. Of course, you can do it in the integer search, but we can also do some other things. For example, integer can be a keyword, key value of a record. For example, student ID, right? And then for this, each of them has a record, contains some other information. So it also can be used for other things as well, as long as we can sort the keys accordingly. Then we can arrange them as a binary search tree. So here you can find that we have a sequence. We call the sequence is K. So this sequence means the order doesn't matter. Sometimes we write like this way: K1 and K2, so on and so forth. So this is a sequence. That means the order doesn't matter. So it must meet this relationship, K1 less, or you can use put equal, doesn't not matter, right? Just this is strictly less. So K1 less or equal to K2, and then so on and so forth. Kn is unsorted keys. Okay, so that means what we can do is only sorting the keys. If they have some additional information, you can put those information in the record, and then what our target is just we want to find that record, but we pre-sorted all the records, arrange them as a binary search tree. So if you have interest in binary search tree, you can go to the I think it's part maybe part 2, part 3. Let me confirm. Yeah, I do have a plan. If we have time, we may cover binary search tree. So that one will be in the chapter 12 in the part 3, data structures. So but here we already cover a little bit. So if we cover binary search tree, we may talk about for example, what's the insertion, deletion, like these operations. But here just understand, okay, we have this binary search tree to arrange the records, so based on their keys value. And then here we talk about the each. That means, for example, you search books. So each time you reach one book, the probability is pi. Probability means the chance. That means how much chance you will find this book. this book, this book. So that means, of course, you find all the books, all the chances, add them together should be 1, correct? So that means how much percentage chance is like a dominate how much percentages. Of course, we need to do a lot of experiments and then find this one. So this is, if it's uniform, there's no problem. For example, each one has the same chance. That will be very simple. But usually we have non-uniform distribution. So that means some records have higher chance to be searched, to be the interesting things for others. But some of them maybe have some of people have less interest in some books. So this is the reason we want to arrange those things in a tree manner. So we want to put the most important ones on the higher levels. So on the shallow level, that means on higher level, like this one. Okay, so let's just use this one. Level maybe we just from 0 to n. Okay, maybe this is better. That means put it on the top because it's easier to reach that item. Okay, but we want to have average, not only just put all of them in the highest, but we cannot arrange them into all of them in the same level, correct? So because binary search tree, each one has only 2 children, so that means each layer, so one node has only 2 children, so we cannot arrange all of them at the same level. So we need to find a way to arrange those keys. Okay, so we want to build a binary search tree, or in short just called BST, with the minimum expected search cost. So this means consider all the queries. What is the minimum average search cost? Expected means the mean value. That means the average. What's the mean value for this one? So each one has a cost. So cost means that how many keys you need to reach before you find. That means how traverse or searched ones. Okay, that means 1, 2, 3. Put here the cost is 3. If this one is 2, if this one is 1. So actual cost is the number of items examined. Okay, for example, if we look at the ki, the cost will be the depth of the ki plus 1. For example, like this one, because the depth means how many layers to reach this element. So this layer 0, this layer 1. But we reach any element in the layer 1, we must start from the root node. So we need to add one more. So same for here. This is layer 2. So reach here, you need to start from here and here and here. So it's one more than the depth, right? So this is depth 1, depth 2. So add one more, just because this is only the depth, how many steps, but you will examine 3 elements, 3 keys. Okay, and the depth of this one is just the k's depth in the BST tree. Okay, T. So we also want to mention, in fact, here there's a little bit of deviation from the book example. So we don't consider, for example, if we search the tree, the elements are not in this tree, right? Not in this tree. So we don't consider that one. Then you can find that in the book we have a Q. So that one is just consider how much chance. If you find the element, yeah, it's 5, 3, 1, but it is it is 0.8 or 1.2. Okay? If like that, that means this one is not in this one, but we have to go this way. So that means we just consider we want to find a key which is available in the BST. Okay, make it easier for you to understand. Okay. So when we have a question, we'll do similarly. We don't consider the Q one. Okay, just consider the Q is the probability for the unfailable keys. So we only consider the probability PI, means the failable one. All the search queries are in the tree. Okay. So here we just give an equation for that expected search cost. Expected search cost, that means average cost. So we already know this is just probability E, means the expected. So E, expected value of this search cost, you can think this is a variable. So what is the average value for this variable? So we want to calculate it. So basically, this one is not a continuous distribution, is distinct. Correct? It's distinct. That means for each of ki, it has a pi probability. And then what is the cost? So we already mentioned is 1 mole of the depth of the ki, and then the chance to reach that key is pi. So the chance to reach this key is pi, and then the cost is this one. Right? Cost is this one. So it's 1 plus the depth of the ki in that binary search tree T. Okay. So we can expand it, this one. So this one we can expand it. This is depth ki plus 1 and then multiplied by pi. So it's depth ki dot pi and plus pi. Then we separate them into 2 summations. So in total we have n keys cut from k1 to kn. So then we have these 2 summations. So for this one is easy because this is just summarize all the possibilities for all the keys, all the n keys. So summarize to be 1. That's all the chances, correct? So all the queries, you search the tree, you want to find a key value. So all the key value will be existing in this tree, and then each one has 1 probability, is some percentage of the chance. So add them together must be 100%. Okay? So that's the total chance. Okay? So maybe 10% for this one, 20%, 20%, and so on and so forth. Add up together to be 1. Okay, to 1. So this one is can be simplified as this one, just 1 plus and depth ki dot pi and then I from 1 to n. This will be easy, correct? That means we just only consider this part. Okay, make this one smallest. Okay, make this one smallest. So that means you need to find a binary search tree, or how to arrange those keys. There's n keys. Because the binary search tree, we can have a lot of arrangement. You can select any of them as the root. Okay? So this is just because even you have decided the root, you can also change the subtree for the left subtree and the right subtree. You can have multiple chances. So because this is the same, okay? So if you choose in the middle, and the left one, you have another subsequence. So how to arrange this subsequence is the same as you arrange the whole subsequence. You also need to choose a root in this subtree, and then continue, so on and so forth. So that means we have a lot of combinations. So which one is the best one? So we'll look at minimum expected search cost. That means we want to find the BST, the binary search tree, which can make this one smallest, be the smallest one. That means make this one the smallest one. Okay, that means after you get the tree and then you calculate this value, okay, this is the smallest. Let's look at one example. That means based on different arrangement of the keys, different BST trees, we have different values for this. Okay, let's look at this one. We have 5 keys, and then the search probability for each of them is as follows. So P1 is the chance to reach the first key, P2 the second key, P3 the third, P4 the fourth, and the last one. So add them together will be 1, correct? 5, and then 75, 95, 100, correct? So that means we have this probability. If we utilize this binary search tree, we want to calculate the expected search cost. Okay, K1, K2, K3, K4, K5. You can find we arrange them in a sorted way, correct? So this one less than this one, and then this one less than this one. So put this one in the here, and then in the middle, and then this one larger than this one. So that's the arrangement. So make sure you understand it. Here that means if we already decide this is root, you can only have 1 node here, and then also you must have 3 nodes here, right? Because K2, K1, K2, K3, K4, K5 is already sorted. So if you find this one, then all the smaller values will be on the left subtree, and all the bigger values on the right. Okay, once you decide this one, this root, you only have 1 here and 1 here. Okay, but of course you can arrange them into different way. You can put a K3 here, okay, K3, and then K4, K5. That's also possible, okay? So let's look at this one. Based on the previous equation, so this is the key index, and this is the depth of that key, so Ki. So the depth for K1 is 1, K2 is 0, K3 is 2, okay? Depth 0, 1, 2. Okay, so we start from 0 because that's the tradition. So that's the depth, how far of the node to the from the root. So root to root itself is 0. This one to this root is 1. Okay, and K3 is 2, K4 is 1, K5 is also 2. So you get the depth first, okay? Because we want to calculate this value, right? So now it's the depth Ki and then dot Pi. So Pi just here, right? So put a Pi here, Py 0. That means this is multiplication, right? So depth, so this one multiplied by this one. So 1, 0.25, 0.25, and 0, P2, so it's 0. And the P and the depth, so this one is 2, and then P3, so 0.1, and then depth 1, and then P4, 0.2, and then depth Pi, P5, so it's 0.6. So add up 10, you get 1.15, 1.15, okay, 1.15, and then do not forget you have 1 plus this one. So the average cost will be 2.15, okay, 2.15. Okay, this is the first arrangement for this number of keys. If we changed to be this one, okay, we still put a K2, but we put a K5, and then all this K3, K4 must be on the left because they are smaller than this one, right? So put this one on the root. So, and then if we choose this one as the root, then you have this K4. Is there K4 answer to choose a 3? Yes, of course, 3, and then we can put it like this way. Can put a K4 here because that will be 3, is 3 is smaller, okay, and then K4 is bigger, and then K5, K1, K2 in the beginning. Okay. If like this way, we do it similarly. Okay, so we do it. K1 is 1, and K2 is 0. K3 is 1, 2, 3. Okay, K4 is 0, 1, 2. Okay, and 5 is 0, 1. And then similarly, we just do the multiplication, summation of the multiplication. Okay, so you get 1.1. So add 1 again, so you got 2.1. So previous one is 2.15. This one is 2.1. So it's smaller. So that means different arrangement of these keys will result in different average cost. So for here, in fact, this is also turns out to be the optimal for this set of keys. But of course, this shows the result. But our target is just automatically find this best binary search tree. Okay, so that will be the algorithm part. Here we give the problem and give example. Just want to introduce the problem to you, the question. Okay, so from the previous two examples, we can have the following findings. The first one is that the best or optimal BST may not have the smallest height. Just look at this one and this one. So this one, the height of the tree is 1 and 2. This one, the height, the optimal, in fact the optimum one, the height is 1, 2, 3. Okay? So that means it does not mean we must have the shallowest tree. Okay, so the shortest tree. So this is the first one. And the second one is that we may not put the highest probability key as the root node. Just look at the best BST. The highest one, in fact, is P1, right? Is P5, but in fact we put a P2 on the root. So this one also put a P2, right, with a K2. So this is that means it seems like not the same as we expect. What's the reason? The reason is that we want to get the expected, not only for the highest one. Right? So we want to get the average. The average is the smallest, not only just put this one on the top, on the root. Because if you put this one on the root, it happens this one is the largest or the smallest, then you may need to search all of the elements in the left or right, in the left or right subtree. Okay? If this one is the largest, so all of this one will be on the left subtree. So each of others will take some more time. So in average, it is not optimal. It's not the smallest. So this is the reason. Okay? We want to have a balanced, at least relatively balanced tree. That means we have nodes on both sides, left and right, rather than just only based on the probability we arrange accordingly. Right? But of course, you can still find that we usually put the nodes with highest probabilities on the shallow nodes, shallow level, shallow layers. Right? So that will be easy for us to find it. P1, P5, like this. Okay. And then P4, P3. Right? But not put the highest one, not less. We must put the highest one as the root. Okay. So next question is that how can we find this optimal BST? So we mentioned before, if you don't have a solution, you may consider exhaustive search. Okay, exhaustive search. So of course that one will be the last method for you to solve a problem. So for here we are talking about dynamic programming. That means of course we want to use dynamic programming, but here we just give the example. If we use the use the exhaustive search, this is just like a search all the possible BSTs and then find the best one. So we need to calculate all of them. Okay? Construct each n node BST. That means this BST, this binary search tree has n nodes. Okay, we list all the possibilities. Okay, how many? Okay, we need to find later. So and then after you get these trees, you will calculate each tree's cost. Okay? So for each assign keys and compute expected search cost, and then finally you find the one with the minimum search cost. That will be the answer. But how many? It will be this. That means lower bound is 4 to the power of n over n to the power of 3 over 2, 1.5. Okay? So this one is very big if the n is very large, because you may search a large data set, a large number of records. So n is big, this one will increase very fast. Okay, very fast. So that means this is not a efficient algorithm. It may have a combinatorial explosion problem. So with the n is big n, it may have a lot of combinations. You may not have enough memory to save all of them as well. Okay. Okay, that means we need to find some other solutions. Okay, this is the example part. Okay. So the optimal binary search tree algorithm have 3 steps. The first step is to find the optimal substructure. So that means so as I mentioned in the previous example for the LCS problem, longest common subsequence. So same, we want to find the optimal substructure. That means how can we find the structure to get the optimal solution for the original problem? So that means maybe a subproblem also have a optimal solution, which is similar like you solve the original problem. So let's look at this one. So assume we already have optimal BST, the binary search tree, and then we have a subtree, and inside of this tree, that means from a root, from a node, and then all the nodes under this root will be the subtree, right? Subtree. So for example, here we want to mention, so all the nodes, all the keys are arranged in a continuous way. So because we already sorted, okay, so this is important. So if we have a subtree, which is here, then it will involve a continuous sequence as well. So that means, for example, is from the ki to kj. Then we also have this subtree is also optimal. So t prime is also optimal. So you can just consider if this one we only cover this one, okay, this value. If we already select the root, then we can say we can cover some keys which is from I to j. So if this one holds, okay, then this t prime must be the optimal. If this one is not optimal, definitely we can find a one which is optimal, and then replace the original one with that optimal one. So we said the proof will be based on the cut and the paste. So we ignore the proof, but we want to introduce the idea. So that means it's like a contradiction, proof by contradiction. For example, if this t prime is not an optimal binary search tree, we can find the optimal binary search tree to replace it, which will further reduce the search cost. Cut. because for those nodes, those keys, the cost will be dropped, will be decreased. So the total cost will be also decreased. So that's why we have this contradiction, which means that it must be the optimal. Then we can say the whole binary search tree is the optimal. Let's look at how to do the formulation for this optimal substructure. Okay. For example, if for this one of the keys in the ki to kj is the root, okay, from ki to kr is the root, okay, so this one must be the root of optimal subtree for these keys. That means involve these keys. Of course, we said here may be not the only one. It's possible you have multiple optimal subtrees for the same sequence for this ki to kj, but they must be the same average search cost, because optimal means the cost is the minimum, can be only one value, right? So let's assume the left subtree of this one of kr contains from ki to kr minus 1. So you can find here must be r minus 1 because already sorted, right? We're sorted, so that's sorted. So all the values which are below kr must be in the left, and the others must be on the right. So assume kr contains left one is ki to kr minus 1, and then the right one is r plus 1 till kj. So this gives us a good malloc, right? For example, this one is we said this subtree is optimal, and then the one is root. So this one is the left subtree, right subtree. So this one also must be optimal one, correct? Must be optimal one. If it's not, we can also replace, cut and paste. This one also must be the optimal one. So you can find is like the optimal substructure is there, correct? So that means when we want to find the optimal structure of the original problem, we find the optimal substructure. So this one is optimal, this one is optimal, this one is optimal, and so on and so forth. This one is optimal, this one is optimal. So under each subtree must be optimal, right? So this is how we solve this problem. Since each subtree is optimal, we can solve from the smallest subtrees, solve them, and then just filling the tables, filling the tables, and then we can expand. We solve this one, and then we solve this one, so we can expand. So that means each time we find a solution for a subtree, and then we can find the solution for others based on the solution of previous. Okay. So to find the optimal BST, binary search tree, we examine all candidates roots kr. So this is the algorithm, that means step. So we assume, for example, for this, if it involves this sequence from ki to kj, so we first select a root. We don't know which one can be the root, so we must loop over all of the possible roots, so from I to j. That's why we had this one. So once we decided the root, we decided the left and the right. How to decide left and right? It will use the same way as we solved the previous one. So this is the idea, cut. Determine all optimal BSTs containing ki to kr minus 1 and containing kr plus 1 to kj. So what is the optimal subtree for the left and also for the right? The same idea, okay, as this one. You also select one as a root, and then divide this sequence into two subsequences, and the left one is left subtree, solve it using the same manner. Right one is another subtree, solve it in the same manner. Divide, conquer, divide, conquer, cut. So this is the idea. But you can find we cannot solve each subproblem independently. We must solve the small problem first. So we build on the solution from bottom to up. Okay, from bottom to up. So we first solve the solutions for the small sequences, subsequence. We build the optimal ones, and that one will be used as answer. So you just fill in the blanks for other subproblems. Okay. So this is in fact finally, once we reach the answer for the original problem, we have solved all subproblems. Okay. Okay, this is the first step for the optimal substructure, and then we continue with the next step 2. Okay. So the second step is the recursive solution. That means we already found the optimal substructure. So next one, how to develop a recursive algorithm to solve that answer. Okay. For example, we assume that means we want to find the optimal BST for the sequence from I to J. So I must be larger than 1, larger or equal to 1, J less than or equal to N. So this is only the sub problem, because in total we have N keys. This is just only solve 1. Similar like the previous divide and conquer, or just the longest common sequence for generalization, scalability consideration. We want to solve any subsequence. So that means that this is general from I to J. So it's only one component. Okay? For example, this is a long sequence. We only chop a segment to solve it. This is to solve any subproblem. And the J must be larger or equal to I minus 1. Okay. So when J equal to I minus 1, then the tree is empty. So this means for this one, we allow the J to be on the left. Okay? That means, for example, if you will reach I and then I minus 1, this is also allowed. The reason is that we want to put this subproblem in position to compose the answer for other problems, because when we reach the bottom case, it may reach that empty case. Okay, so that means we allow the right side is on the left. Okay, so J is larger or equal to I minus 1. So here we define EIJ. So like the previous slides, we mentioned about the expected search cost. So for the same meaning, we use E to represent the expected, okay, search cost. So we want to solve this one, okay? That's our main target. Once we got this one, we can reconstruct the tree. So this one will be our final goal. Just want to find the EIJ. So this is just a table. Okay? For we want to solve any subsequence solution. Solve then find the optimal BST for that subsequence. Okay. So this one is for the expected search cost of optimal BST for Ki to Kj. Okay. And then we want to, so our target is that we want to find a equation. Okay, we mentioned in fact. So the most important thing for dynamic programming is we need to find a recursive equation. Once you got a recursive equation, write in the code, implement the solution, write the pseudocode, implement the pseudocode in the algorithm. It will be very easy. So the most important is that we find a relationship between the original problem and the sub-problems to find that equation. So for example, for here we already mentioned we allowed the J is less than I. So if J is equal to I minus 1, you don't need to bottom up till some other value, till this one is already enough. Okay, so J equal to I minus 1. That means if it is smaller than 1, less than the I. Then this cost will be 0 because the tree is empty. Of course, the expected search cost will be 0. And if j is larger or equal to I, of course you can allow the single node as well, single node tree, just one node. Okay, so j larger than I, then we can select a root. So this is just based on the previous optimal structure, substructure. So we need to loop over all the possible root. So we can select one root from this subsequence I to j, right? For some I less than r, some r which is larger or equal to I and less or equal to j. And then next one, you will recursively make an optimal BST. So that means you already selected a root. So next one, you want to find the optimal solution for the left from I to r minus 1 and the right from r plus 1 to j. So that means how to solve this one, you will say recursively, because you got two trees, two subtrees. You want to find the optimal BST for these subtrees. You will use the same method to solve the whole. Whole is what? From I to j, cut from I to j. So that means for the I to r minus 1, we want to find the optimal BST. Recursively make an optimal BST for the left subtree as well as for the right subtree. Okay, so this is the structure of your pseudocode. Okay, structure of pseudocode you will solve in this way. Okay, solve like this way. And let's look at next how to write the equations for the EIJ. So here we just want to find that recursive equation. Okay, based on the previous slide, we already know how to get that solution. So you will solve the left and the right. Okay, you choose any root and solve left and right. And once you get left and right, you will need to compose, calculate the EIJ. Right? You solve this one, how to use the answer for this one and this one to get the answer for EIJ. Okay? This one we already know. This one is EI r minus 1. So this one is ER plus 1 to j. So your solution will be just based on these two, find the EIJ. Of course, you can use some other unknown things, for example p. Right? Okay, let's look at how can we get these equations. Once we get this equation, then we'll be able to do the implementation. Okay, let's look at. So we already have we assume we already got the answer for the left and the right, right? So if we already find the left or right, so we call it is optimal OPT, optimal subtree. If the optimal subtree becomes the subtree of a node, so that means we will draw it before, kind of like this way. If this optimal subtree becomes a subtree of a node, then we need to, so that means that this one is already solved, and then we want to compose the answer for this one. That means how can get this one from these two. So EIJ, this one is only consider the subtree itself. So that means we don't, there's no, this one is already the root. So that means if we cut and paste, for example, this one already solved, and then paste it here. So we put this one under this node. So all the depths, all the nodes depths will be increased by 1, right? Because we put under this one. So that means initially is 1, and then it will be increased by 1. So of course, if you put this one under another node, it will be increased again. So that means we just, the first step is a recursive way. So depth of every node in the optimal subtree goes up by 1. And then what will be the cost to reach any node in this optimal subtree? so will be increased by some amount, okay? Because you can just look at the previous, what is the definition for expected search cost, okay? So let's go back to here, okay? To here. So you can find expected search cost is based on the depth and the probability, right? So this is the depth and then probability multiply. If the depth increased by 1, so the cost will also be increased by the pi, right? So this one increased by 1, so it's d plus 1. Now it's d plus 1 plus 1. Then of course will be increased by pi. So that means it will be increased by its probability. Okay. Let's go back. Okay. So that means expected search cost will be increased by all the numbers. All numbers will be increased. So you can get Wij equal to L from I to J and then PL. So that means this optimal subtree, of course here we just put this one in for any general one, the ij. That means assume the subtree contains the keys from I to j. So of course if it's only from I to r minus 1, then you just use r minus 1, correct? If it's r plus 1 to j, then you use r plus 1 to j. So that means accordingly, which subtree, what are the numbers, and then all the numbers in that subtree will be increased by its probability. The cost will be increased by its probability. Then this is the total cost. So in fact this one is based on this equation we put here. We want to mention again, so we don't consider the node, the keys are not in the tree, so we don't consider this one. This one is just the keys, not the query are not in the tree. Okay, we just only consider this part. Okay, so if KR, for example this one, if KR is the root of optimal BST for KI to KJ, so that means we go back to the previous question, if like this way. So we have a left subtree, right subtree, and then we put the left, we already solve this one, and then we put this one under the root of KR. So this one we get the KI to R minus 1. This one have another subtree, is from R plus 1 to J. Okay, so all of this one will be increased by its probability, this one also by its probability. And then what is the search cost? What's the solution for this optimal BST for the KI to J, the whole, okay, for the whole, okay? So we can get this. So it will be the first one is the root node is the cost, okay? We reach possibility, we stop there, and that's the probability for there, okay? So it already find the answer. And then you may just reach the left or reach the right. If we reach the left, so this is the optimal subtree cost, optimal cost for the subtree itself. But if we put this subtree under the root, under this one, under root KR, then it will be increased by its cost. Okay? We said it's from I to R minus 1. If the subsequence is I to J, then you summarize all of them. Okay? You just summing all of them together. So here is the subsequence is only from I to R minus 1. Then we do summation from I to R minus 1, and then it's probability. So that means add all the additional cost once you put this subtree under the root KR. Similarly, for the right subtree, this is without just itself. Okay, itself is a tree, and then the cost is er plus 1. So you can find here is the recursive, because we can solve this one first. Okay, so er plus 1 is a subproblem of this one to j, and then we similarly we add its additional cost. When we add this subtree as the right subtree of the kr tree, tree with the root of kr. So this is the most important equation for this problem. This one shows the recursive relationship. Okay, so once you get this one, you can just solve the small problems, and then you get the answer for big problems. Okay, so this is the idea. So eij, we don't, you can find it, this one you just don't loop over or anything. You just solve the cost first, and then you will reconstruct the tree again. So for this one, in fact, we can further simplify it. How to simplify? So e something we cannot simplify, but we can put these three things together. So will be PR. Put this one in between. So I to R minus 1. This is R plus 1 to J. So this one, based on this one, we already know this is like a sigma from I to R minus 1, and then PL, and then we put a PR in between. Right? And then we have a next one is this one. So it's sigma L from R plus 1 to J, and then PL. So you can find we do the summation, right, from I to R plus minus 1, and then we plus PR, and then R plus 1 till J. So in fact we add all of them together, right, from I to J for all the possibilities. If like that, we can just simplify it as Wi to J. So this is the final answer to solve EIJ. Okay, solve EIJ. Okay, that means how we solve this one, we just use this method. Okay, this method. So that means once we decide R, the root, then the optimal solution for the original problem can be calculated by the addition of the two sub-problems answers plus the Wij. So the left sub-problem, the right sub-problem answer, and then plus the Wij. Okay, this is only just consider all the nodes, all the search queries are inside of the tree. But since we cannot we don't know which one should be the root of this solution for the I to J, right? So that means we can only try all the possible roots. So this one we already mentioned before, the optimal substructure. Okay, since we don't know the KR, so then we need to find the minimum one. So choose a KR which can get the minimum one. How to get that one? So this will be the solution, right? So R can be any keys from I to J, and then if we decide R, so the EIJ will be this one. So just get here. So we find the minimum one. Okay, minimum one, as long as I is less or equal to J. Okay, but if for example this one we already mentioned before, it also allowed J is less than the I. So we put this bottom case in the equation as well. So we get the, if J is equal to I minus 1, then it's 0. So it's possible you reduce a problem, you will get that one. Okay? For example, you only have one node, and then you have a left and right, or you have two nodes, so you have only left or only right. So like this case, it will have an empty one. So that means we put that one there. Okay? Put it there. Okay. If it's 1, 2, okay? So you have to choose the 1 as the root, and then 2 must be on the right. The left one is 0. Okay, left one is 0 to 1, and then 1 to 2. So 2 to 2, 0 to 0. Okay. So this is the second step. That means the recursive solution to generate a, in fact, recursive solution we mentioned just like you need to find an equation, equation among the subproblems based on the optimal substructure. This is also how you take the problem. So that means that we, based on the answer, we generate a solution, based on answers of different problems. So how to get that one? Of course, you need to go over the problem to find the optimal substructure. What's the optimal substructure? So that will be this one, We mentioned the previous as well. This one, just like this one. Okay, the subproblem. Okay, this is the second step, just a recursive solution. So last one we just do the that means once we get this one, we want to get the answer. Okay, so now we continue with the third step. So the last step, also the third step for the optimal BST tree is how to compute the optimal solution. That means we already know the relationship between the big problem and subproblems based on this optimal substructure. Then how to calculate the EIJ? That means, of course, you can calculate any result from one. Finally, you want to find out from 1 to n. So that means you need to calculate just populate the values in that table. So that means we start from here and here, and then we can cut here. Here you get the last one. So that means you need to calculate. How to calculate? So you only have the equation, but you need to implement a pseudocode, algorithm to calculate this one. Okay, let's do that. So we define some variables first. So for each subproblem ij, we store the expected search cost in a table E from 1 to n plus 1 and 0 to n. So this is just like the table size. So the first one is the row 1 to n plus 1, and then this one is 0 to n. So in fact we already know we want from 1 to n, 1 to n. So it should be 1 to n is enough. Why we use 1 to n plus 1 or 0 to n? So this is just also for the bottom case. If you, based on the previous equation, you can find we may just add one more or minus 1. So we want to find that bottom case. Okay, bottom case, put that one. But usually for those cases, it's easy to solve. Easy to solve. So you don't need to consider a lot. So just of course you may just further expand, but it's not necessary. So it runs to n plus 1, runs down to 0 is already enough. Okay, because we only use the entries for EIJ, well, j is larger or equal to I minus 1. So that means only one less, at least one less than the I. So that I to j is in the front. And then when we search the EIJ, we also want to save the root node, because that one will be important for us to reconstruct the solution. So for this reconstruction we didn't cover in this slide, but it is in exercise. Okay, if you have interest, it will be the 15.5 and /1. Okay, bar 1. So that means for this exercise, once we got a solution here, for EIJ and also root IJ, you need to reconstruct the solution. So similar like that, we reconstruct the LCS, longest common subsequence, so you can also find the answer easily. Okay, we ignore that part. We just only cover the EIJ and the root IJ. So this is root of subtree with the keys from I to j for this subsequence in the 1 to n. And this one is the sum of the probabilities. That means all the possibilities will be summed together. Okay, this is from 1 to n plus 1, 0 to n. All the possible possible keys. And then if, for example, j is less than I, one less than this one, of course is 0. We mentioned it before, right? And this one is we can also just using this equation with sum the probabilities from I to j. Also can you sum first from I to j minus 1 and then plus additional one, the last one is j, right? So based on that equation we already mentioned before. So this is holding. Okay, let's look at the pseudocode. This is our final result. Okay, pseudocode. So the pseudocode you can find so the input is p, q, n. So in fact, even you ignore this one is okay, because this one you can find the code does not contain q. Even we calculated w, we didn't have q, can only p. So this is just want to be consistent with the paper, with the book. So q for that one is just consider the keys are not available in the BST. But in fact, we just only consider simple case. So all the search queries are inside the BST. So it's only just P and N. P is of course is a sequence kind of from PI to P1 to PN. N is the number. That means that those number of keys. Okay. First one we do the none from none 1 to 3 is for the initialization. So for I from 1 to n plus 1, we do this one, ei I minus 1 equal to 0, and the wi to I minus 1 also equal to 0. So this is just only for the, you can find it's initialize, can initialize the table. Okay, initialize the table. So like this way, I minus 1, because this is 1 and then 1 less, so it's this one, right? And the w also you have just like you have a 2 w, right? So this one is what we want to have, but this one you also just bottom case you put 0. Okay, so this is just for initialization. And then next one from 4 to 13, this one we find the answer for E1n, but find the E1n, we find all the other problems answer EIJ, right? So here let's look at, so that means you can find here we not solve the problem directly, so we examine all the possible subsequences. So consider all trees with L keys. So you will just build on smaller ones, for example only 1, only 2, only 3, and then you approach, grow till you get n. So this is the idea. So that means all trees with L keys, L can be 1 key, 2 key, till n keys. Okay, till n keys, then you expand. Okay, expand the tree, 1, 2, 3, until you get all of them, cover all of them. Then so that will be the final answer. Once L reach n, then it will solve the final problem, our original problem. So with n keys. But we mentioned before, okay, it's like working on a table. You need to solve the small problem first. Okay, if L is 1 to n, so here with that we want to find the optimal solution for the tree with L keys, kind of L keys. So for this one, L keys, that means the length is already fixed. So must be L, L, L. But where is the starting, where is the ending, we didn't know, right? We already mentioned before. So all the keys have been sorted. So once you sort it, if you have a tree only cover L keys, must be continuous the way. They must be in the continuous way. So you only need to decide the starting position, right? Starting position. Once you know the starting position, you will find the ending position because the length has been fixed. Okay. So this is how we do that. We use this one to find the starting, this one find the ending. So starting position can be 1, starting from the first one, or till here. So you have a sequence. You can start from here, L, but the last one must be here, cat. So you cannot go further. So you have L keys here. So this one will be n minus L plus 1. N minus L plus 1 will be this one, correct? N minus L plus 1, and this is n. In between you have this one minus this one, you have L minus 1 plus 1, so have L nodes, exactly L nodes. So this one will be the rightmost position for the starting key, okay? Start key, first key of the subtree, okay? With L nodes, L keys. And then once you get this one, you can find the ending position based on I. That will be much easier. Just add the deviation. So I plus L minus 1. For example, from 1 to 3. So you have 2, add 2, but in total you have 3. So this is like 3 minus 1 is 2. So that means add length minus 1, length minus 1 for deviation. Okay, then you already decided the starting position and ending position. This is a subtree from I to J. So from I to J, we want to solve this one. How to solve this one? We already give the equation, Eij will be this one. So you will loop over all the possible roots among the Ij, and then calculate it in a recursive way. Get this one, correct? Okay. So you can find it here. So how to solve this one recursive way? In fact, the recursive is inside because you will solve the from 1 to n. So once you reach the L is 1, you solve all the possible trees with 1 keys. And then if you solve the next one, all the possible trees with 2 keys. So all of the sub-problem have been solved. So that means that this is the idea for the recursion. We don't call the question itself, the method itself. In fact, we solve it in a recursive way. We solve a small problem first, and build on the small problems, we can get an answer from big problems. Okay. So we initialize this one to be infinity. Why? We want to do infinity because we are doing minimization, correct? We want to find a minimum. So we initialize this Eij to be the maximum, and then if we find a smaller one compared to the previous one, we will replace that Eij with the smaller one. So this is why we want to initialize to be infinity. And the Wij, we use the prefirst I to j minus 1 and then plus pj. So this is just because we increased the subtree size by 1, but this Wij has ij minus 1 has been solved before, so you don't need to do that summation again. From I to j, you sum all of the values again from beginning. But I to j minus 1, this is just the one less, the size of the subtree is one less than the current one. So this one has been solved in the previous L, because this Ij decided the length of the subtree. So this one is already solved. Just like you have a okay, you want to add one more, then you just add one more. No need to start from the first till the end. Okay, so this is just initialization. Okay, initialization for E and W. So next one, we just loop over all the possible roots. R can be any value from I to j. So we decided the subsequence is I to j, this subtree, right? I to j. And then once we decided R, we can use that equation. We can calculate the tree, the trees, the optimal binary search trees cost based on the equation here, based on this one. So it's left subtree, right subtree, optimal solution plus Wij. Okay, that's here. Left, right, and W. So this we put it as a t, is temporary value, because we want to compare this one with the pre-first EIJ, because we loop over all of the R, so we search the minimum. This one is calculate the minimum. So this one we calculate with another one which is solved before. Every time we examine whether the current one is smaller than the previous one. So we loop over all the possible roots. We choose anyone as the root and then find the solution. We compare with the previous one, previous solution EIJ. If the current one is smaller, we replaced the optimal solution with the current one. This is T compared to EIJ. If this one is less than the previous optimal solution, we assign the current one to be the optimal solution. And also we load down the current root to reconstruct the optimal subtree, optimal BST tree for the original problem. So that means if we know this root, then we can reconstruct. We decided what's, because we decide all the roots. If we decide all the roots, of course, from 1 to 1, 2 to 2, so you can build up the subtree, build up a tree for the origin problem. So this one seems easy. That will be the exercise we mentioned before. And after we loop over all the possible sub problems, we reach the N, and then finally we return the E and the root. So that's the final answer. The E is all the tables. In fact, the last one from 1 to N, we already find the if we have 1 to N, then that will be the answer. And the root will be will capture all the roots of all the subtrees, and then you can reconstruct the answer. Okay, so this is the idea to solve. That's also the last slide. So the time complexity for this one is n cubic. So you can find this is n, this is n, this is n. So you can this is n. So you can just do summation, 3 summation together, and then you can find finally it's n cubic. So compared to the previous one, if you use the exhaustive way, it's exponential, more than exponential. So this one is cubic, so it's much less computational complexity. Okay. Okay, this is the optimal binary search tree algorithm. Is another application to apply the dynamic programming into solving this problem. Okay. So overall, you can just use one sentence to conclude. So basically, we first composed a recursive relationship between the big problem and small problems, and after that we find a way to calculate the original problem by solving the small problems first and approaching progressively. So from the top left and to the right bottom. Okay? So approaching progressively. So to reach the answer of the original problem. Okay, this is also the last thing I want to mention. Okay, and think this is also the end of this one. Okay, this one. So in the following ones we already covered in the previous video. So you may already learned. Okay, this one just do some conclusions. Okay, analysis. So you have learned that one before. So this one just want to add one more problem, one more example for enhancing your understanding, because dynamic programming is also important algorithm. Okay, that's all for this chapter.